Good morning, everyone, and I appreciate your attendance and attention. It's a privilege to talk to this group, and I'm looking forward to your questions and the follow-on. I've learned a lot from the two presentations I've been able to see so far, and this is quite a hot topic these days. I got back from the Hanover Messe 3 or 4 weeks ago, I guess, and I think the word model in that environment has been completely replaced by digital twin. So about every time you turn around, there's some instance of a digital twin in some context. So it's certainly a topic for discussion. It's very foremost in the mind of the Chips for America program. In fact, there was a workshop a few weeks ago on standardization of certain aspects of that, and I'll cover some of that late in my presentation. And there's actually another workshop next week rather, that was going to be in Boulder, Colorado, that's now going to be virtual for those that are interested in the whole standardization process. It's a standardization readiness workshop. There's a framework for evaluating both technology markets and community in the standardization process, and there'll be a workshop on that topic. I think there are probably close to 300 people registered for that, and if folks are interested, I can post a link to that registration site as we go here. So, all right, but let's jump into operational digital twin for semiconductor manufacturing. I'll explain what that means here in a minute. For those that aren't familiar with PDF Solutions, we're a software company based in San Jose, California, but with people all over the world, probably 500 plus employees now in all the regions where semiconductors are manufactured. We focus on data and analytics with software platforms that, and combined with a great deal of services to help people accelerate yield ramps and maintain that, and process improvement, et cetera, et cetera. So we're deep into the factory level software business. My heritage is actually with Symmetrics, which is a wholly owned subsidiary now of PDF Solutions. We were acquired about 3 years ago, and we're in the connectivity and control business, principally for the equipment suppliers, but also with factory connectivity solutions also. So PDF Solutions has been the factory level software, and we provide a lot of the plumbing from the equipment up through the systems to enable real-time data to flow into those applications. My industry heritage actually comes from Texas Instruments. I started as a summer student way back in 1972. I was in the design automation department back in the era when we were working with 2K microcontrollers for microwave ovens, and so it's been a privilege to see the evolution of this industry over the past 50 years, and I thought it was a miracle this stuff ever worked when I first started, and I still believe that. So it's fun to have seen that evolution, and I'm fond of telling people that if you get bored in this industry, you're just not paying attention, because there's something exciting going on all the time. So in the more recent, I've spent some time also in TI's industrial control division, the PLC division. And so I know a lot about embedded control systems, but spent a number of years at Semitech, and was part of the startup team there in the late 80s, early 90s, and then left to be part of a process control company that was eventually acquired by KLA-Tencor, and then worked with Symmetrics for the last 15 years. So it's and throughout that process, for the last 20, I guess I've been involved in the 30 years actually in the industry standards. So I spent a lot of time working with the semi-standards community. I had the opportunity to spend some time at SRC, visiting during the early years of Semitech, when that was one of the centers of excellence that we worked with. So I have some familiarity with Research Triangle Park and the SRC. So, and my formal education was at Rice University in Houston. Another sort of fun fact is that my first office at TI was in the materials building, which was not a very nice place at the time, but it happened to be the place where Jack Kilby's office was. So I had a chance to meet him in that era. And at Semitech, for a number of the years, Bob Noyce was the CEO before he unfortunately passed away. So I had the privilege of working both with both of the two co-inventors of the integrated circuit. So that was another fun fact. All right, am I coming through loud and clear? Okay.
Yep, perfect.
Okay, good. Yeah, let me know if some echo pops up. Sometimes that can happen.
Sure.
All right. Well, we can't start a discussion of digital twin without a definition. And this is the one that we use. Again, there are a number of them out there, and they're all fairly similar, but this is the one that provides the context for what we call an operational digital twin. It's a virtual representation of an object, a system, or a process that can provide intelligent feedback when integrated into some system that needs to talk to that entity. Those applications can be forecasting, simulation, optimization, root cause analysis, real-time control. That's actually one of the favorites. We've been doing this a good while. Intelligent feedback to the physical world with some form of simulation, emulation, or analytics. AI has taken a big role in digital twin architectures and implementation in the past 5-6 years. So that's also a very hot topic in the industry today. The pieces that enable a digital twin are listed below the line there. All the documents that are associated with behavior of something, its design and implementation. For things where you want to actually see into what's going on, whether it's a process or a piece of equipment or a factory, 3D representations are one form of digital twin. Of course, there has to be a model, a digital representation of these things that you can create and encapsulate and share. Simulation, of course, is a big piece of it. The earliest examples of digital twins, I think, in our business have been some of the real-time process control systems that essentially had a model, not a first principles model, but a heuristic model of the behavior of a process that you could sort of back solve and put delta results you wanted to see in and know what settings to change. And that's gone by a number of names, but it's now actually referred to as a digital twin for a process control environment. Of course, keeping humans in the loop with visualization is an important aspect of this, and keeping these models accurate and accurate reflection of the real world incrementally as new information becomes available. So synchronizing the models with the actual real world is an important component. So these are pieces of the digital twin system, if you will. All right, what PDF Solutions has posited here is that we really need an operationally focused digital twin for the entire semiconductor manufacturing supply chain if we're going to effectively lash all the pieces of this manufacturing process together. And when you look at how many companies are involved in making an end device, and of course in the individual chips that go into those devices, what businesses they're in, how they're scattered across the world, trying to imagine a way of integrating all that together is mind-boggling. And there are a lot of course, industry standards that help solve some of those problems, but stepping back and looking at that big picture is quite an undertaking. And so being able to bring together data from process and device development through manufacturing, through tests, through eventual deployment, and knowing exactly what went into every device from the raw silicon or substrates, ingots into the final device is the challenge. And the data management for that, of course, is huge. Hang on here. Of course, the best source of data is the actual manufacturing equipment and test operations that are going on, rather than some after the fact or sort of manual reentry of that. And so the real-time integration with all components of the manufacturing environment is important. There are industry standards that deal with with a lot of that, but there are, of course, many challenges still to come in that area, and that enables multiple parties to actually contribute to and be part of this digital twin ecosystem. So again, I'll say more about industry standards later, but the first industry standards in the industry, really all we had to agree on was what the diameter and thickness and orientation of the wafer would be. And I think the first one was a 3-inch wafer back in the 70s. We crossed the threshold of the 1,000th semi-standard about 4 years ago, and that process continues to evolve to support the needs of the industry. Okay, so I've got that picture blown up a little bit with some sticky notes on how different pieces impact this environment. One, of course, is you want real data from every imaginable source, and that includes the manufacturing execution systems that run a factory, enterprise data that talks about orders and replenishment, design data, customer data, equipment data, and all of those things factor into a digital twin system. One of the components that PDF has is what we call a virtual IDM, or independent device maker, essentially a fab simulator that knows how to generate realistic data for all of those sources that can be used to drive whatever component of that system is thought of as a digital twin rather than a real time component. And so we have ways of stubbing out pieces of that whole environment and plugging in digital twins into that virtual simulator as needed. Of course, standards, again, I'm going to hit this topic a number of times. The most important standards are the ones that deal with communication to and from equipment. There's multiple generations of that. Standards for test information, that's what RIT-DB is. Traceability standards, that's what E142 is. I'll talk more about that, but that's the standard that enables us to actually track all of the steps that went into manufacturing and assembly of an independent device. And we have people involved in that standardization process at many places. In fact, Symmetrix's entire business was founded on helping to evolve the standards and then building implementation products for equipment suppliers, in sync with that evolution process. The data collection, of course, being able to use those standards and communication technologies to get information from all the sources, regardless of their adherence to some standard or another, is important. We have a variety of tools for doing that, both standard components as well as edge devices that bridge the gap between what the supplier has provided and an actual standard, and then scalable sort of servers at the higher level that enable that data collection and distribution to support a gigafab kind of environment. As we've dealt with essentially models of processes over the years, and one of the best examples is the fault detection and classification models. These are multivariate statistics models, not first principles models that you use to see if an equipment has failed or is about to fail. And these things are developed by characterizing good runs and bad runs and sort of knowing where the boundaries are between those things, and then applying, collecting real-time data from the process, putting it through those statistical models and seeing, what the results are. The problem with that approach, of course, is that the operating point of the equipment determines, which model you have to select. And for a complex process, a complex piece of equipment, depending on the recipes and the devices and the levels you're running, there may be thousands of actual statistical models that you must choose from a library for a given situation. And when you think about managing that environment in a gigafab situation, a gigafab being something with 100,000 more wafer starts a month, it's quite a challenge. And so having packages that allow you to manage that diversity of models with all the different ways you can select them and update them is a challenge in itself. And so we've been working in the multivariate model business for a long time, and the kind of models you have to deal with in AI and machine learning environments is really no different. Of course, there are integration points between the physical world and the digital world, and vice versa throughout this whole process. Pardon the acronyms. OSAT, for those that aren't familiar, is an outsourced assembly and test facility. So these are the companies that take a finished wafer and then, like a foundry, turn that into the packaged devices. So finally, supply chain traceability, making sure that people can share this kind of sensitive information across a global system infrastructure is a security issue that's foremost in people's minds. And so, being able to handle that aspect of it while doing everything else is just adds another piece of the puzzle. Okay, this is going to sound a little bit like a commercial, so pardon that diversion. But again, PDF Solutions has been, in the business of supporting yield prediction and management and fault detection and analysis for decades. In fact, one of the CV in this context stands for characterization vehicle. One of the earliest innovations of PDF Solutions was designing devices that could tell you, and including those devices in either the scribe lines or other parts of the circuit, that could tell you very reliably what the yield was going to be. And so rather than trying to deduce that from whatever device structures the customer was putting on there, PDF designed special characterization vehicles that combined with special measurement metrology and analysis software that did a good job of doing yield prediction independent of the sort of actual device structure. And so that was one of the core innovations of the company, and that has built from there. Of course, we have a secure data exchange network. There's a product we call DEX, which is deployed at all the major OSATs and across the globe. We have very strong presence at the top tier of those OSATs. One of our companies has been in the traceability business for many years with a product called ALPS, which was an assembly line controller that essentially did this single device tracking. The principles in that organization have been key in evolving the E142, which started as a wafer mapping standard to tell you where the good die and the bad die were, into a whole data structure and ecosystem for tracing exactly where a device is on its and when it leaves a wafer, it goes into a lead frame, goes into into a package, and then into a system. So the E142 is the data structure that supports that kind of traceability. And all the different pieces of analytics framework have been pulled together into a thing called Exensio, which is essentially an analysis platform that spans all sorts of different analysis using design data, manufacturing data, test data, assembly data, and even supply chain data. So this is the label that's given our sort of overall system for this. And we've expanding that now into an AI model ops platform that allows people to sort of bring their own information to this environment. Okay, so when we step back and look at how again, pardon the commercial there, but trying to make the point that we've been in the business of handling digital twin kind of information for our customers for many years, and now we're collaborating with other parties to think about how those things should be re-architected and standardized to provide the sort of interchangeability and interoperability of pieces of it. So these are the list of ILIDs, if you will, the architectural requirements for looking at a digital twin framework that would support a multi-party ecosystem. So this is not something that any one company can handle. So being able to have portable and reusable solutions is key. Interoperability, I'll talk a lot more about later in the standardization process. Again, interchangeability and making sure that the boundaries this is architected in a way that digital twin boundaries are understood and respected so that it can be a plug and play sort of environment. The maintainability is key, and what I mean by that is having the digital twin models evolve incrementally as manufacturing data is collected so that they stay a true reflection of the physical world. And that sort of relates to the next one, is that there should be analytics technology that enables you to do that, not just sort of architectural capability to do it. And then being able to extend digital twins outside of a factory into an entire into the entire supply chain is a big deal. And again, the acronym here, model-based process control, is one of the examples of a digital twin that's been prevalent in the industry for many years. Okay, let's move ahead. Come on. All right. Yeah, I guess the one of the best examples of a digital twin has been some way of predicting the behavior or the characteristics of a device on a wafer without actually doing the physical measurement process. So one of the peculiarities of this industry is that you can't always tell from the process what happened. You actually have to measure the result in a separate step to know how well the previous step did. And if you could eliminate that step, you would save a lot of capital expense and cycle time. And so one of the dreams in the last 20 years has actually been systems that could reliably predict the results of the device just from looking at information from the process equipment that did it. And that's been called virtual metrology. We've had a lot of success in certain domains of that for the past 10, 15 years. And those kind of models have been deployed in what's called skip lot processing, selective metrology. So you determine when you want to actually do physical metrology based on how close the last predictions were. predictive maintenance. You use really the same data, not to predict the device characteristics, but to predict what the remaining useful life is for that equipment before doing some sort of PM on it. The same thing with testing. Full device test takes a lot of time, and if there's a way of knowing that you had a good device without actually going through a test, then that saves you time and money. And yield prediction models, of course, are very important in understanding what sort of material you need to release into a line to meet the actual customer commitments. And so all of these things depend or can leverage a good predictive capability in this virtual metrology area. And it's the model ops architecture is what we have now to actually develop those models and deploy them and manage the plethora of them that exist. Okay, what that's all put into is an actual platform architecture that, again, that not to sound too much like a commercial, but the point of this architecture is enabling components from partners, customers, and third parties to work together. This is not intended to be a hermetic, closed system. And again, the scope is too broad for any one company to handle this whole environment. And so one of the examples I wanted to share about, how one of the earliest examples of a digital twin is this thing we called model-based process control or run-to-run process control. Essentially, you have both feed-forward and feedback algorithms. You measure, you process process equipment 1 here. You measure the results of that to see how it did, and then you can take the results of that and feed forward to the next process because your outputs are going to be its inputs. And so these models you can back solve them to say, we were a little bit off here, so we need to change the settings of our next run based on how far off we were. And that could be the next run of the process you just did or the next run of the downstream process. So that's where the feed forward or the feedback comes from. And for a while, people, the original implementations of this were SneakerNet and spreadsheets. And then, in the 90s, people automated this process and developed these feed forward and feedback models, put the data collection in place, and the evaluations of the models to be able to do that in an automated fashion. And now this is this is really considered an essential application in every manufacturing environment. The error budget for an individual process is so narrow that you can't let any of them drift, or you'll never have a working device out the other end. And so this sort of digital twin of a process model is running in really every factory in the world today. And it's ironically, this was originally thought to be sort of bad science by people that thought first principles models were the only way to go. And it was labeled as automated tweaking and all sorts of other negative connotations, but is now an application that is very well accepted and was, again, an early example of a digital twin. I'm not going to dive into this into a great deal of detail, but just to show how many pieces of a smart analytics platform have to be there to support this environment. When you step back and look at the big picture of it. But again, it depends on good data coming in from the left side and good interaction with actual human beings on the right-hand side, and all sorts of management of information and models in the middle. So let's see. Yeah, this is kind of a way of encapsulating the the evolution of sort of reactionary control to sort of forward-looking control. Again, it's where people talks about where people would be on their sort of analytical scale, and if you look at the last versions of the technology roadmap for semiconductors, we have moved from sort of reactive to predictive sort of technologies, and analytics is a big piece of that. And so most companies find themselves in the middle. We're beyond just reacting to what happened, but we're a long ways from actually being able to prescribe what we should do to get the results that we want. We're kind of in that middle zone, and maybe for a good while. But this is a vision for how to apply all the different analytical techniques and to achieve the right hand side of this picture. Okay. So this is the sort of supervised machine learning is one of the use cases for the model ops framework. And so it shows where we take data from a whole variety of sources. Oops, yeah. Oh, I got an echo. Oh, okay. So there's a whole training process. Those that are familiar with the machine learning life cycle, there's a lot of the problem deals with getting raw data, prepping that, feature engineering, coming out with a candidate model, training and validating that model with multiple cycles to see, how well it behaves. And again, there's a picture that I didn't include that I can put in later, but it shows, how much of the effort goes into this whole data wrangling process before you can actually apply an ML technology. I mean, all the pieces that surround the actual machine learning piece are probably 80 or 90% of the total effort that goes into it. And when you try to scale that to an entire enterprise of data scientists working together on these things, just the management of all those models becomes the biggest part of the challenge. So this is the structure that we've put together in this model ops framework. And there are the key pieces here are the bring your own algorithm and bring your own model, because we've defined these things in a way that allow customers or third parties to retain their intellectual property, to not expose it to the system, and still benefit from the management of it all, to take that, to reduce the effort required for that part of the problem. And so dealing with the leading semiconductor manufacturers in the world, they are very, very careful about their intellectual property. And so they want to make sure that the pieces that touch their secret sauce are encapsulated in a way that is not exposed to their competitors or to anyone else. And so this provision for incorporating customer input into the system was a fundamental requirement from the outset. And so, and of course, continuous integration process, making sure that these things can be updated on the fly after deployment is key. Okay, let me skip this one. It's really kind of a similar. It's another way of looking at the picture before. I probably should have had this slide earlier in the deck, but it, for people that are, I mean, this audience has been doing deep dives, and so this may seem pretty basic, but to a layperson explaining the analogy of the physical world of a road, the digital twin, which is its map, and the applications that allow you to use that geographic information and do something useful with it, is a comfortable analogy for most people. But when you think of how that translates to semiconductor manufacturing, it becomes far more complex. But the basic structure is the same. You've got a physical world mapping to a digital representation, and applications in a given context that deal with some portion of that. So, okay, of course, each one of these things is actually a link to articles that talk about the challenges of looking at a supply chain, a global supply chain. And I won't go into each of these, but these make the point of how important traceability is to this environment. Okay, let me shift gears. I'm going to talk a little bit about the standardization aspect because, again, what I think we're all looking for is a way that we can participate usefully in whatever our specialty or whatever our domain is, without having to understand the whole picture. And so knowing how to model and implement our piece of this puzzle and rely on the other people to do the rest of it is key. And so the CHIPS Act management folks had an interoperability workshop some weeks ago in DC, Baltimore actually, and these are some of the slides that I presented as challenges for the interoperability piece. Again, I mentioned semi-standards. If you look at the 1,000 semi-standards plus that we now have, they span, every imaginable aspect of manufacturing, from safety to physical integration to the actual substrates and devices to communications. The piece that's most important for this interoperability discussion are the ones I've highlighted in blue, the communications and metrics. When you look at the range of semi-standards that apply to what's called smart manufacturing, and again, a loose definition of smart manufacturing is the intelligent use of data to manufacture products, and we've been doing that in this industry for decades. Digital twins is just the latest instance of a standardization category that we have to look at. Let me skip this one. When you look at the connectivity standards, these are the ones that actually allow you to get information to and from equipment. They span probably 30 years of work, from the most basic serial communications to all the standards that enabled fully automated 300 millimeter manufacturing to the latest generation that enables multi-client data on demand, the ones called EDA or Interface A. EDA in this context means equipment data acquisition, not design automation. So it's an unfortunate choice. But if you look at the challenges of digital twin standardization, these are some of the biggest issues to deal with, interoperability, and what I focused on in the NIST workshop a few weeks ago was looking at interoperability and what we can learn from existing standards that we have done that apply directly to digital twins. So the areas to focus on are making sure that the application domain of a digital twin is well defined and understood, because this is what allows you to encapsulate the behavior in a way that can be substituted for something else. Of course, metadata model elements, how do you actually represent that domain explicitly with information technology, and then rules for taking a metadata model and constructing a specific instance, how you can discover what another system has electronically or in an automated fashion, and then of course the security, access methods and privileges for that, interaction scenarios and data sharing, and the technology stack that would be useful. So these are the areas that if you truly want to have interoperating digital twins, have to be agreed upon. And so the example that I used was this EDA set of standards where multiple pieces of equipment can talk to multiple clients in a secure session environment without knowing anything about each other sort of a priori. And the key is, first of all, having secure sessions so that an equipment knows who it's allowed to talk to and vice versa. Having a set of services that allow the metadata to be requested so that as a client, you know what all you're talking to and what data is available, and then having mechanisms for, given that metadata model, specifying your data collection requirements in a way that can be satisfied by the equipment in real time. So this is a fairly complex suite of standards that, again, enable real-time discovery of the metadata, real-time definition of the data collection requirements, and then real-time satisfaction of those requirements by the equipment. So it's a complicated standard that I think has lessons for digital twins. The metadata model, of course, has a static structure which reflects the physical organization of the equipment, and then all the dynamic behavior that's in that equipment, composed of events, state machines, parameters, other behavioral elements. These two things together form the metadata model for the equipment. The other, and these are some of the node types that allow you to actually specify what happens in a piece of equipment, not only the physical elements, but also ephemeral ones like a job, things that come and go, and material that comes and goes, but has to be associated with the equipment. So these are this kind of physical and logical structure has a direct analogy for digital twins. The other big concept was the data collection plan concept, which was a data structure that describes a whole wide range of data collection requirements, from conditional sampling to events to alarms. Everything you might want to get from a piece of equipment, you can describe the requirements in this data structure. And then, of course, there was a whole generation of experience that went into recommendations for what a good structure would look like. So the first pass at these things was fairly ugly until you had a generation or two of experience, which then turned into another standard. So I guess the key point is that you never get these things right the first time. Standardizing anything as complex as a digital twin is like cooking pancakes. The first one's always going to be ugly, but you don't get to the second one without the first one. And so the key is to make an attempt, put it out there, and get to the versions 2 and beyond as quickly as possible. So again, looking at the lessons from the digital twin that come from the EDA standards, we agreed on the scope, we agreed on standards for metadata models, we agreed on access methods and the actual data collection scenarios and the technology stack. So all of those things had to be nailed down in a standards context for a piece of equipment and its clients to interact effectively. The same will be true of digital twins. These are all the kind of things we'll have to agree on. So that's what I had prepared. I'll take questions as long as you've got them.
Thank you, Alan. Looks like there are a couple of questions, comments in the chat.
Yep.
I think Gil had some. Gil, you online? Would you like to ask that, or you want me to read?
Yeah,
it?
I'm online. I had to step away for a while, so I'm not sure if these have already been answered. But
no, not yet.
Or if I'm not sure if this can be answered. But I'm wondering, anything? Can you tell us anything about your biggest customers or working examples? You gave some names, just to say, how. And then the other thing is, do customers share or collaborate, or is every service that you provide firewalled completely from all others?
Great questions. Well, our customers are all the ones on the top 10. So the Samsungs, the TSMCs, the Intels, Global Foundries, IBM. We've been in business long enough to where we have customers all over the planet. in every region, in China, Japan, Taiwan, Korea, Europe. So yeah, and they're customers not only of our services, but also the platform itself. As from the Symmetric standpoint, and this is the division I'm part of, the connectivity and control software. We probably have 300 different equipment supplier customers with software in every 150, 200, and 300 millimeter factory in the world. So the customer base is essentially the industry. So
okay, so you probably have
as far
examples of what, like, this IP sharing model, right? I mean, obviously some stuff has to be shared and some stuff we won't share.
Yep.
I'm just wondering, what that looks like in a simple block diagram, if that's possible. But I'm sure it's quite complex, right? But basically, you would be able to tell companies, okay, this is what we recommend in terms of sharing and not sharing.
Yeah, I think so. And what frequently gets shared, and the some of the most energetic meetings every year are user group meetings, where we essentially bring customers together in an environment where um, they actually sort of self-select what they're going to share. They all regularly share requirements in terms of, hey, I don't like this, or this is something I want to do. Can you help us? And some people are free and open with those. Some people don't, because it kind of telegraphs, the the latest problem they're trying to solve. But what we have is a very vibrant sort of user community that that ends up sharing in sort of birds of a feather sessions, which is really the way you want it. And from my Semitech years, I remember the events that were the most highly rated were the ones where we essentially provided the coffee and donuts and the agenda and the pro forma. Here's the topic we want to discuss, and let the member companies, in the current case, our customers, share their best practices. And so, as far as uh, we learn from our customers about the capabilities that are needed to go into future versions of these systems, and that is pretty openly shared. As far as specific, recipes, devices, characterization vehicles for a given process, all that's pretty private. But the equipment and the software that deals with those specifics is fairly generic, and so it's a good balance of competitive and pre-competitive. So,
All right, thank you. I should have mentioned that
okay.
this is Gilroy Vanentop from Intel asking the question, but thank you.
That's no problem. Thank you.
Right. I think we have Sadhus and then David Robertson.
Yes, I have a question. Is there one specific application you can show that essentially is more recent?
Recent. Let's see. Well,
Because it's hard to gauge appreciate all the detailed pictures, but not able to get to grasp what essentially has changed from the last 20 years, for example, other than the interoperability standards and things like that.
Well, the interoperability standards still have a lot. They've got a long way to go. I mean, we're just in the digital twin context. We're just scratching the surface. I think the biggest recent change, two, one is more of an architectural change where having data flow into this. Let me find a picture that maybe talks to it personally. Okay. This is not very product specific, but the pieces that we have focused on in the last few years are the big data infrastructure, if you will, moving from a sort of a purely network-based approach to a cloud technology base. where the scalability of data collection and ingestion and management is now on a footing with the sort of gigafab requirements, and so collaboration with and use of Amazon Web Services and cloud computing technologies has allowed the scalability of that aspect of the system to be much improved. The other big change.
So
the other big.
Can I actually pick up on that? Because
sure.
I think the Amazon cloud services probably may not be a good solution, because there's IP related issues on manufacturing line. I don't know whether companies, I can see startups using AWS and things like that, but established corporations would want to have more control of the data, right? Or am I missing something?
Yes, there are on-premise and off-premise and hybrid architectures for all of those that address that concern directly. And so, yes, there's a hypersensitivity to data security in this environment, and so the places where the most private data is dealt with will be entirely an on-premise installation. But that doesn't preclude the use of all the high availability, microservices architectures and Kubernetes management systems for incremental scalability and all that. So the Amazon Web Services and the Google Cloud Services and the IBM Azure, Microsoft. I'm getting confused here. All of those technologies have on-premise installation options that address that directly. So the other big change has been this whole model management environment where rather than kind of dealing with them at an individual application level, treating model management as a major system requirement in handling those for the variety of applications that might need hundreds or thousands of models. That piece has been a big focus. And so
just as a FYI, these things were very relevant 20 years back too, and including, so just as a FYI.
Okay, thank you. Great question.
There's David Robertson. We got 1 minute.
So Dave Robertson, Analog Devices. I really appreciate your painting this picture and the perspectives of digital twin as a mechanism for factory control and kind of yield optimization and really running this. The other place, one of the other things that people are talking about digital twins for the manufacturing lines is ability to do what if experiments, or I'm trying to introduce a new process into the factory. And will the factory be able to support me trying to construct a device this way, or change the process steps in order to introduce some new feature? Is that a completely different digital twin? You talked a little bit about the empirical models, and in my experience, empirical models are better at interpolation than extrapolation. Each model gets tuned. The more you can tune the model to a specific use case, the better. What happens when we try to drive this thing off road? Is that a completely different digital twin, or is there, how do we harmonize those different needs?
Yeah, I don't think it's, the individual expression of that need for extrapolation, could be a separate digital twin, but it would fit in the sort of overall system that you had already. And so the hope in being able to standardize or agree on the boundaries of these things and standardize those interfaces would allow you to plug in an extrapolation, a brand new model for something into its manufacturing context and see what it did, and without changing the rest of it. I mean, that is the holy grail of plug and play, is to be able to do exactly what you describe. And so, no, I don't. I think the scope of the newness of that would be well bound, and should be stated as a pretty clear requirement too. That's a great use case. So, yeah, I don't think that should upset the, unless it was an entirely new process that impacted, let's say, multiple steps. If it was a well-defined improvement in a well-bounded area, then there shouldn't be a big
Running
issue.
virtual what-if experiments is within the boundary of the problem definition here.
Absolutely. In fact, that's a great deal of what we end up doing is providing simulation models for either equipment or processes or procedures in a way that they can be substituted sort of invisibly with the real process, and the rest of the system shouldn't know the difference.
This is Andres Torres from Siemens. Just a quick question. Have you looked at CFX from IPC?
Yes, I've looked at CFX. In fact, personally, I've looked at it in a fair amount of detail. It's a fairly prescriptive, fairly rigid standard for for very specific data collection use cases in the PCB world, and it has in our connectivity products, we have a sort of plug-in placeholder for CFX should it start to be required by any of our customers, but as yet we haven't had to implement it. We've prototyped it just to see how compatible the technology stack is with the other semiconductor communication standards, and it's easily plugged in. But the semantics of it, again, are fairly rigid, and until we have a specific factory request for that, it's just on the back burner.
Okay, thank you.
All right, so
Yep.
looks like, yeah, we're almost 4 minutes over. Ganesh had a question or comment from Purdue, so would you mind answer that?
If you have time, if not, it's
Yeah,
okay.
if you have time. Yeah, Alan?
Oh, I'm fine. I've got nothing on my calendar for the next half hour. So,
Okay.
What's the question?
I appreciate very much the breadth, the presentation, Alan, was very informative. So it's somewhat related to the earlier question. So you had a simulation box, and I was curious what fraction of the data that is generated comes from simulation, if there's some way to put a percentage on it, or what fraction of the data originates as simulation data that then gets replaced by empirical data.
Actually, a small. The simulation box, I think, is I think if it's one I think you're referring to,
Right.
it had more. It had which slide was that on? Let me make sure I'm answering your
one of the first
right
2 or 3 slides.
Okay.
That one.
Here?
Yes.
Okay. Okay, there's a couple of contexts to that. I'm going to be okay. In the physical, for a physical device like an equipment or a component of equipment, we can actually simulate 80% of a device's behavior, whether it's a FOUP indexer or a vacuum robot or a part of an EFIM or pieces of physical equipment. We can simulate a lot of that with actual physics-based mechanical models, and visualize that in a very realistic way, and then at some point just replace the simulation physics with the real devices. And so that there's high fidelity in that part. I think the characterization vehicles, which is the technology that PDF has developed to simulate sort of process behavior and results. That's probably a pretty high percentage also, because that's kind of first principle stuff. When we're talking about simulation at a factory level to essentially provide a kind of a working factory to drive multiple processes to see how those would integrate, that's probably pretty low percentage, because it's just enough to make sure the process interactions are valid. It's not going to be high fidelity compared to a real factory. And so it kind of depends on which physical device you're talking about, and what the percentage of simulated behavior versus real applies here. Did that sort of answer the question?
That very much answered the question. That was, I guess, my thought was more on the equipment level, and your ballpark number of 80% was very helpful. Thank you.
Yeah. Okay. Yeah. Yeah. No, a number of our, I mean, we've been in the equipment communication control business for 35 years. And so, we know a lot about and a lot of the physical components are the same. Mass flow controllers, RF power generation, chucks, FOUPs, robots. A lot of those components are common, regardless of the process you're implementing. So we know how to drive those things.
All right.
Thank you.
I think that's really good talk, Alan, and
Good.
thanks for answering all the Q&A.